electricity. And remember, I talked about how we saw forces and then we saw fields. A force we can find by Coulomb's law. It's the interaction between two charges. If I have two positive charges, they're going to feel a force that's repulsive. If I have a positive and a negative charge, they will be attracted to one another. We've sort of seen charges at work. I think that you have an intuitive sense of how charges are attracted or repulsive. Yes, intuitive, maybe? Yeah. Fields are probably not so intuitive. Fields are really just a tool that we use to describe the force that charges feel. It is a force per unit charge. And then voltage, which we're going to get to today, our potential, are similar, that we're going to see that voltage is an energy per unit charge. And so before we get into voltages, let's define what is potential energy as it refers to electricity. Electric potential energy, or potential energy, describes an object's capacity to do work. We've seen this all along, right? We had this with gravitational potential energy. This object has gravitational potential energy, so it has the potential to do work. It has the potential to have a force over a displacement. So we can have a similar thing with electric potential energy because they experience these forces. Then they have the capacity for motion. So for example, if I have two positive charges that are here, they're going to feel forces that are in this direction. So if I hold those two charges in place and then I let them go, they're going to zoom away. Just like the pencil, if I hold it here and I let go, it's going to rush towards the earth. So electric charges can also have the potential for motion when there are two or more charges. We can describe this work. This work is force times distance. We've already seen force. Force is kQq over r squared. Right, that's Coulomb's law. So this part is Coulomb's law. Oh yes, D. You're right. Sorry. Oh, you have your white out. All that. You're ready to go. kQq over d squared. And then if I multiply that times d, then notice that one of these d's cancels out. And so I'm left with an expression for work or potential energy. So this is work, and that's equal to potential energy, which is kQq over d. That is our expression for potential energy. And if I'm looking at two charges like these here, the distance d is the distance between the two charges. That's d, and then the charge on them is q and q. So if I increase the charge, I increase the potential energy. What happens if I take those charges and I move them farther away from one another? How does that affect the potential energy? Before you answer, we can look at the equation and we see that d is in the denominator. And so if I make that number get bigger, that's going to affect u. But think also, if I take those charges and I move them farther apart, what happens to the force that acts upon them? It gets smaller, right? Because they're farther apart, they're just affecting one another less. And if they have a smaller force, that means they have a smaller potential for motion. And so they'll have a smaller potential energy. We see that flesh out here in the equation, that if I increase d, I'm going to decrease u. If I move them farther apart, their potential for motion will also decrease. If d goes up, then u will go down. It's an inverse relationship. So here we can have positive or negative potential. Not potential, potential energy. Let me put this in quotes. So it'll be important that we keep those in mind because we'll see potential a little later and it's different. So U is potential energy. We can have positive or negative potential energy. Two like charges have a positive work. or a positive U, let's say U, you have to do positive work to bring them together. And our work is equal to our change in potential. So we saw this a chapter or two ago. This is kind of a difficult idea, but I think you're starting to get it. If I have two positive charges, I have to apply forces in this direction to move them together. Because they're always trying to fight against it, right? They're trying to go apart. So I have to apply a force in this direction to move those charges together, right? And so am I doing positive or negative work to take two positive charges and move them together? I'm applying a force in this direction to move the charges in this direction. Did you see me sigh just a little bit? If I'm applying a force in this direction, and I'm moving the object also in this direction. If our force and our displacement are in the same direction, that's a positive work. If they're opposite directions, that's negative work. Okay, so if I'm moving two positive charges together, I have to apply positive work, a force in the same direction as the motion, in order to move those two positive charges together. And because I've done positive work, I've changed my potential energy by a positive amount. They have positive potential energy. But we see that in the equation, because if Q is positive and Q is positive, then U is positive. Or if Q is negative and Q is negative, then U is also positive. The negatives would cancel one another out. Okay? What happens if I have a positive and a negative charge? What's going to happen to the work that you do? I have a positive and a negative charge. Now these two charges, instead of being repulsive to one another, they're going to try to get to one another. You have to hold them back in order to move them closer. And so I have to apply a force in that direction in order to make it move in this direction. So am I doing positive or negative work? Negative. Remember, it's like the two dogs that are trying to bite one another, and you have to pull them back, and they're still moving closer to one another. You know what I'm talking about? Yeah. Okay. So you have to do positive work to bring them together. If they have opposite charges, there's a positive and a negative. They're going to be attracted to one another. So you have to apply a force that's opposing the motion. They actually do negative work. Oh, no. Yeah. They do work on you. Do I like the way that? Yeah, I'll explain. Because they experience an attractive force. And if you think about the positive and negative charges, you can think of these. What are these? Those are dogs, yes. And one's positive and one's negative, and you're holding a leash right here. They're not people, they're dogs. They're very poofy dogs. I have them on a leash, and I have to exert. The dogs are trying to get at one another, right? They have F dog. They're trying to get at one another. So you have to exert a force in this direction. And so you're actually doing negative work on the dogs as they move towards one another. So our displacement is in this direction. You're applying a force in the opposite direction, and those two combined give us a negative work. Okay? That all goes to say that when I do negative work on these charges, that it causes them to have a negative potential. But we see that anyway, because if one is positive and one is negative, then it's going to have a negative potential. All right, we'll look at some problems a little bit later in the old test to see how I'll quiz you on that. And the book also, it goes into that a little bit more. That's probably one of the more difficult topics. So I recommend that maybe you put a star next to it and go back and reread that section in the textbook too. And if y'all have questions, think about it, come to me, or ask me next class period. We can talk about it some more. Alrighty. Both force and energy decrease as the distance increases. Am I? Remember, force was kqq over r squared, and energy, U, is kqq over r. So both of these will decrease. There's an inverse relationship as the distance increases, though at different rates. Right? F is proportional to 1 over r squared. U is proportional to 1 over r. So for example, if I double r, I have quarter of my force. I quarter my force. But if I double r here, I have half of the potential energy. So if I move them farther apart, I have a quarter of the force, but I have half the potential energy. Because one's an inverse square, and one is just an inverse relationship. However, when D is very, oh, I'm sorry, y'all. D. So sorry. When D is very large, Megan, did you get that? D.
I was writing D.
When D is very large, that means when D basically approaches infinity, that's what the arrow means, that D gets really, really, really big until it's basically as far away as you can go. What happens to U and F when D gets really big? If I make this number really, really big, what happens to this number? It decreases until eventually it equals what? 0. So when D gets really, really big, both F and U are 0. So if I have a negative charge and a positive charge here, they have forces that are relatively big, and then as I move them farther and farther apart, their forces get smaller and smaller until finally, when I move them farther apart, they're basically no forces at all. They're just non-existent. Okay, and that happens pretty quickly. I say when D goes to infinity, but it's not really infinity. In fact, it's a value that is dependent upon the magnitudes of the charges. So it can just be a meter or a couple of meters. But we'll just talk about D getting really big. Charges move in electric fields. Remember, we talked about this, that if I have an electric field like this, and I have a positive charge in it, what is the direction of that positive charge? It'll feel a force in what direction? Is it going to feel a force in the same direction as the electric field, or in the opposite direction of the electric field? In the same direction. So charges, positive charges, feel a force that's in the same direction as the electric field. What if it was a negative particle? What would be the direction of the force that it would feel? It'd be the opposite, right? So here my positive charge is going to move to the right. But if I had a negative charge right here, it would move in the opposite direction. And that'll be important later when we talk about cell membranes and the like. But they also prefer to move in the direction of decreasing potential energy. and like a ball rolling down a hill. So for example, we've talked about this before, but if I have a mountain like this, and I have an object on it, a positive charge, it's going to roll down that direction. And so that's analogous to the positive charge moving in the electric field. So over here, I have high potential energy, and over here, I have low potential energy. And that's true, right? I mean, that's the same as what we saw before with gravitational potential energy. That this is my position of high potential energy, and this is my position of low potential energy. Think in gravity, right? mgh. When h is 0, our potential energy is 0. As h goes up, our potential energy increases. You can think about it the same way with a charge. That if I have a positive charge, it will move from high to low. And in a similar way, this guy right here is moving from high potential energy to low potential energy. So this positive charge is at a position of high U, and it moves to a position of low potential energy. Just like a ball rolling down a hill, no different from that, except instead of talking about gravitational forces, we're talking about electric forces. But they're very, very similar. They basically respond in exactly the same way. However, notice that with the negative charge, it moves the opposite direction of the positive charge. It's actually moving from low potential energy to high potential energy. Negative charges just do the opposite of what we would expect charges to do. We don't have an analogous thing for masses. We don't have a mass that moves from low potential energy to high potential energy. What would a mass look like if it were to move from low to high potential energy? What would it be doing? It would be like setting a ball on a hill, and then it would do what? It would roll uphill. And we just don't have that. We don't have objects that will on their own move from low to high potential energy. But negative charges do that. So a negative charge, it would start here, and then it would move uphill. Negative charges, they just do the opposite of positive charges. That's true in everything. They're the opposite of positive charges, and so they always do the opposite of what positive charges do. And so here, it moves from low potential energy to high potential energy. And so our charged particles in the body, they'll do a lot of the same. So they will move from areas of high potential energy to low potential energy. All right. I'm going to make a little caveat here that these are positive charged particles. Positively charged particles, because negatively charged particles, well, they'll do the exact opposite of what positive charged particles do. This is probably new stuff. Like, even if you've seen some of the previous material that we've done in physical science in high school, you probably didn't do much electricity. Is that right? Electricity in high school at all? Nobody's admitting. Did you? No? Huh?
I didn't have this in school.
Okay, yeah. It's important, though, because the nervous system is based on these. Like, electricity actually comes up a lot in what you guys will be doing, especially in the nervous system, and then also in some of the instruments that you'll be using in your various allied health fields. All right, let's try this first one. We're doing the one on the left. Objects move in a direction in which their potential energy does what? All right, let's stop at 35. 35. Okay, good. B is right. That they'll generally move so that their potential energy, like on a mountain, will decrease. Though negative charges will do the opposite of what our positive charges do. But in general, objects will tend to do this. So it decreases. Hey, do y'all ever get cold in this room? Some of you have jackets on. You ever get cold? Yeah. If you ever get cold, I tell you, the best spot to go is right over here. Like, this is the warmest spot in the room. It's like 90 degrees over here. You get it? All right, let's try the one on the right. The electric field is the measure of what per charge? All right, we'll stop a few seconds. 38. We should be getting 100% on this question, okay? The electric field is the measure of force per unit charge. Force per unit charge. Make sure you know that you're going to have probably a couple of questions that ask about electric field and electric potential, just a basic understanding that field is a force per charge, and then potential, we'll see in the next section, is energy per charge. Make sure you remember that. Force per charge for field, energy per charge for potential. And then potential energy describes what's the same as what we've been doing, the potential to do work, or the potential for motion. All right, so electric potential. We'll often use the word voltage for this. Those are mostly the same. As far as we're concerned, we'll call them identical. That voltage and electric potential are the same. So when you talk about the voltage of a device, a 9-volt battery, 120 volts in your house, that those refer to the amount of energy that you're giving to the charger. Okay? Electric potential is a measure of the energy per charge. So we'll define it as U over Q. And remember our three big ideas. We have F, E is F over Q. And now we have V, which is U over Q. That's force, field, and potential. And be careful, it's not potential energy. That's something completely separate from potential. They're related, but this V is potential, and U is potential energy. So if you need to make some flashcards or whatever, but make sure that you keep those separate in your mind. They're all very similar, forces, fields, and potential, because they're all interrelated. They're all related to one another, but they're different. So students sometimes get confused between those 3 or 4 different ideas. This is measured in volts. And as I said, we have some different ways of talking about it. We can refer to it as potential, voltage, or potential difference. They're similar, and they're a little bit different. It's nuanced. This is the energy per charge at a particular location. And these two, voltage and potential difference, are the difference in energy per charge between two different locations. And often we'll call this delta V, which is, V2 minus V1, the difference in two potentials, whereas we just call this V, because it's just the potential at a particular location. I tell you that because later we'll develop an expression, we'll have an equation for V, and we'll talk about delta V when we get to our cell membranes, that there will be a potential difference between 2 points. One on one side of the cell membrane, and then on the other side of the cell membrane, there will be a potential difference. And we'll see that charges will move in one direction or the other across that potential difference, just like they move with a field line or against a field line. Okay, questions? Do you have any questions now? This is kind of tricky material, and it's sort of new to you, and there are lots of variables that look similar, and equations that look similar, and ideas that are similar. So I just want to make sure that y'all are understanding, but you're also going to need to spend some time just digesting it yourself. Questions, though? Why don't we go to the back, and we'll ask some questions. Let's go to the practice test in the back. Oh, let's see. We're looking at exam 2. I think, isn't this, or is this exam 3? 3. All right, I used to do 4 exams. All right. Let's try number 25 here. So exam 3, number 25. Which of these has units of newtons per coulomb? Potential energy, electric potential, potential difference, electric forces, or electric fields? Which has the units of newtons per coulomb? Think what those units are measures of, newtons and coulombs, and then, you know, we have our 3. What are their units? What are they measures of? Oh, come on. What is newtons a measure of? What is newtons? Force, and then coulomb? Charge, right. So I'm looking for something that is a force per charge, which is a F over Q. Which of those is a measure of force per charge? Hmm? All right, let's stop at 150. 150. Okay, that's a little better than you were before. So it is electric fields. That an electric field is defined as F over Q. F is newtons, Q is coulombs, F over Q, that is electric field. Let's try number 26. A positive and negative particle experience a force that is what?
So Q always means charge.
Q always means charge. And sometimes we use lowercase q, and sometimes we use uppercase q. Same thing.
And coulombs is that expression KQQ over D.
Coulomb is just a measure of the charge. Yeah, but it is the same.
Is that equation kind of measure, or you would?
No, it's
describe?
it's inherent to the material. So all materials have 2 things that describe them: their mass and their charge, their intrinsic qualities. All right, let's stop 57. 57. Very good. A is right. That's an attractive force, positive and negative charges. Let's see. Let's try number 22. The sodium atom has 11 protons. How many electrons does the sodium cation have? Did I tell y'all my sodium joke? Nah. Were you just shaking your head? Oh, that's a good one. All right, let's stop at 40. 40. A cation is positive. Yes. So this would be a cation because I have fewer electrons than protons. This would be a what's it called? No, not a neutron. What's it? Was just normal. I don't know. I don't know what a chemist call it. Neutral. Yeah. This is neutral. I think it has an official name. I have to ask my chemist friends. And then this is a anion. Okay? Cation, neutral, or anion. Well, let's try number 27. Here I have some cubes that are either attracted to or repelled to one another. And I want to know which of these situations is now correct. Based on what we know on cubes 1 and 2 and cubes 1 and 3 interacting with one another. Which of these is correct? One and 2 are attracted, 1 and 3 are repelled. How are 2 and 3 to interact with one another? All right, let's stop at 118. 118. Stop at 122. All right. So look, it doesn't really matter what the charges of them are. You just want to pick one. And I'll say, like, for example, 1 is positive. And if 1 is positive, or I could say that 1 is negative, it doesn't really matter. But if 1 is positive, what is 2?
Negative.
It has to be negative. And so if 1 is positive, what is 3? Positive. And so if I put 2 and 3 together, they're going to be attractive because 2 is negative and 3 is positive. Or if you want to do it the opposite, I would say 1 is negative, that would mean 2 is positive. 1 is negative, that means 3 is negative. And so 2 and 3 would be positive and negative. It doesn't matter. Really what matters is how are they acting towards one another. Are they like charges or dissimilar charges, opposite charges? So C is right. You'll see similar questions on the old test. Make sure that you're able to go through that process and ask, are these like or opposite charges? Let's try number 28. And if you finish 28, go on and do 29. I know we haven't done nerve cells, but should try it anyway. Number 29. But right now we're doing 28. This is for 28. might want to ask yourself the question first is the force going to increase or decrease? I'm moving these things closer together. What happens to the force? And then based on that answer, you can eliminate at least 2 or maybe 3 answers. I'm going to write down the expression for force. Remember, force is KQ over what? D squared. Does that help you? Okay, let's stop at 135. 135. Okay, that's better than you had before. Before you all had D, but the answer is E. Huh? There is, yeah. Let me show you this first, and then I'll show you that, okay? So if I have this, that means I get over 1/4. But that's the same, if I divide something by 1/4, that's the same as 4 times. But you're right that there is another equation that's very similar. In fact, there are several equations. I'll go and write them all here. We have F equals KQQ over R squared. Then we have, what do we have next? E is KQ over R squared. Then we had V, or no, we had U next, didn't we? We had U is KQQ over R. And then next, I don't think I've given this to you yet, but V is going to be KQ over R. So we have 4 very similar equations. They're all in your equation sheet, but you'll need to be able to sort them out in your mind. That you know this is force, field, potential energy, and potential. Let me write those out. Force, field, potential energy, and potential. And potential. I'm going to put in parentheses also potential difference and voltage, because those are similar terms that we'll use. Note cards help on this. Make some note cards, flashcards or whatever. Make sure you understand these big ideas. Don't memorize the equations. You have the equations, but make sure that you understand the difference between them. And notice, too, that these are inverse square relationships, and these are just inverse relationships with R. D. Excuse me. Okay? That's D. The distance between the charges. Let's do number 29. We haven't gotten to set nerve cells yet, but y'all should be able to answer this. I have a potassium ion, a cation, and it's going to move in a particular direction. Which direction is it going to move? Is it going to move this direction or this direction? That way it will move out of the cell, into the cell. Does it just not move at all? Or does it stay in the middle? Does it just sit here in that cell membrane? I have a cation, potassium cation. Okay, doing pretty well. Let's stop at 55. We'll see that with the transport of these atoms, that there are several different things at work. I think I heard somebody say concentration. Did I hear somebody say concentration? Yeah, there is a concentration gradient that causes ions to move from one part of to the other. But then there are also electric forces that cause them to move. And actually, the electric forces are even more important. And so if I have a positive particle right here, it's going to move in this direction, because it's going to be repelled from the positive charges on the outside and attracted to the negative charges on the inside. Let me ask you another question. If I were to draw the electric fields, what would the electric field look like? Would the electric field be up? Would the electric field be down? Or would there be no electric field on this? Would I draw the electric field going in this direction, or would there be no electric field at all? Would the electric field vector point up, down, or no electric field at all? We talked about how to draw electric field lines early on in this chapter, and that's sort of what this is getting at. What is the direction of the electric field? Okay, let's stop at 58. 58. B is right. It's going to be down. The electric field will always move from positive to negative charges. So the electric field in my cell will move in that direction. Okay? Let's ask another question. Oh, and I also want to point out here that this is a positive charge, and the positive charge feels a force in the same direction as the electric field. At which of these locations, A, B, or C, is the electric potential or the potential energy? It would be the same for O. At which location, A, B, or C, is the potential the greatest? Let me write that. Which location is V or U the greatest? I'm about to start. Yeah, A, B, and C are your answer choices. At this location, outside the membrane, inside the membrane, or outside, at the membrane, or inside the membrane, inside the cell. Which location is V or U? They're related, right? V is U over here. Which of those is that the greatest? Bless you. All right, let's stop at 45 or 47, let's say. Okay, A is right. Listen, I understand that some of you feel like you're always in the red on these questions. Don't be do some of you ever feel that way? You don't have to answer. But I understand that some of you always feel like you get the red, that you never get the green. That sometimes you want the green, right? Just hang in there. Like, missing these questions, not a big deal. Answering the questions is a big deal. But missing them, not a big deal. You're still going to get all your class participation as far as the credit in the class. But these questions are good places to get them wrong. Okay? Yeah. Yeah, can I answer this question? Okay, and then I'll go back up. So, at the location where it's the greatest, I have the highest potential here and the lowest potential here. In fact, if I were to draw my mountain, it would look like this. Uh-huh. Yeah. So here, my positive charge has a high potential, and it moves down in that direction. And, in fact, since V is equal to KQ over R, KQ over D, excuse me, I have a positive V here, and I have a negative V here. And then here, I basically have V equals 0. So I have my biggest potential here, and then it moves down. That's why my positive charge moves in this direction. If I had negative charges, not for a clicker, but if I had a negative charge, what direction would it move? Up, down, or stay stationary? it would move up, right? Negative charges do the opposite of positive charges. It would move up. It would move from the inside to the outside. It would be repelled from the negative charges and attracted to the positive charges. So all these ideas are related. The fields, the forces, thinking about a negative charge is attracted to the positive charges, and then the change in potential. All those different ideas are related to one another because they're all based on Coulomb's law. They're all based on the idea that charges experience forces. That was true for gravity too. That all those ideas that we were working with, F equals mg, F equals ma, all that business, that was all related to Newton's law, universal law of gravitation, that g mm over r squared. All right? All right, let's go back. We're going to introduce potential. Practicing the old tests is a good way to prepare for the quiz. As I told you, it's no secret. I pull the quizzes straight from those old testing quizzes. And for that reason, I want you to go and just sort of practice those things. Now, your tests will be new questions, but they'll be very similar. So as you prepare for those old testing quizzes, that'll help prepare you for the exam, too. So a good way to do this is just print out all those tests or quizzes as you're reading through your chapters. Try to answer the questions as you go along. It'll help you to remember what you're reading too. All right, so since potential is energy per charge, all right, that's how we define potential. It is U over Q. So since this potential is energy over charge, we can develop this expression for the potential of a single charge. So this is U over Q. Remember, U is K, Q, Q over D. And then we divide that by Q. And that gets rid of this Q and one of those Q's. So now we have this new equation for V, KQ over D. I gave that to you earlier, but that's sort of the fourth equation that we'll deal with. And it is on, it's on your equation sheet. All these are on your equation sheet. Even your basic ideas of the electric field and the electric potential, those are on your equation too. That electric field is F over Q, and V is U over Q.
What's the K again?
Oh, the K is a constant. K is called Coulomb's constant. I've never asked a question about it. I don't expect you to know the number. Though the number is 9 times 10 to the 9th. But you don't need to know it. You don't even really need to know what it's called. Just know that it's a constant value. Oh, yes. So, sorry, that's very confusing. If I have 2 lines, that's an equal sign. If I have 3 lines in mathematics, do you know what that means?
No.
It means it's defined as.
Oh, that was a mistake.
No. It means that it's not that V is equal to U over Q, though it is equal to U over Q, but it's that I'm defining this variable as this relationship. So you can think of it as an equal sign. It still means that they're equal, but it has a greater meaning too, that this is what I'm defining something as. Okay? 2 signs? What's that? What about 3? That seems like we should, like a sign for, what? Like a gang sign. Is this? Y'all aren't in gangs, are you? It's defined by, right? All right. So if Q is positive, the potential is positive, and vice versa. So if Q is negative, if this has a negative charge, that means this is negative. I would have a negative potential. This refers to if I have a charge at some location from that charge, a distance d, the potential is equal to kq over d. And at some location from a negative charge, if I have a negative charge at a distance d, that potential is equal to kq over d. But here, q is negative, so v is also negative. So if I have a negative charge, it has a negative potential surrounding it. Remember how we talked about fields? How we use fields to describe the force that particles feel when they come close to that charge, when they come in the vicinity of that charge? The potential is a similar thing, that we use the potential to describe the energy per unit charge that other charges would feel when they come into interact with that charge. Megan?
For the negative v equals k, negative q over d. I just want to.
Like, is this something?
Yeah.
No,
No, is that like you have the negative, or that's in negative v?
Yeah, that's just saying that this value is negative when this value is negative. That if q is negative, v is negative from the equation. If I have a negative number on one side, I have a negative number on the other side. Okay? It's probably the most difficult material we've had all semester, right? This voltages and forces and fields, probably the most difficult. But, like, y'all are some of the best students we have at Nichols. So I know that y'all can do well at it. Right? You know what you have to do to do well. You need to practice the old quizzes. You need to read through the chapters. You need to review the notes. Don't take your head back and do it, for goodness sake, okay? 30 minutes a day, 45 minutes a day. You can get to this. It's not above you by any means. You're certainly not. You're intelligent people. You're capable of doing this. You're certainly capable. You just need to spend some time with it. Further, if D is large, V is what? Small. Right. It's an inverse relationship. If Q is large, V is large too. So what I've just said there is that V is inversely related to D, and V is directly related to Q. If D goes up, V goes down. That sort of makes sense. If I move farther away from a charge, the potential energy I have gets smaller. As I move down a hill, my potential energy decreases. If Q goes up, V goes up. Often, we're interested in the potential difference. Usually, actually, it is the potential difference that we're interested in because we're looking at how particles move from one spot to another. And as I said, when we get to the nervous system, that will mesh because you'll see particles moving back and forth, back and forth. And the reason they're moving is because they experience a potential difference. And this potential difference is just the difference in potential between two different locations. Sorry, I'm going to sit down. Is that okay if I sit? I'm doing a 5K this weekend. I haven't been running in a couple months, and so I just went out this morning to see, am I going to embarrass myself when I do? I'm doing this refuge 5K they have this weekend, and I don't want to embarrass myself. But everything went okay. Like nothing broke. I was doing okay. I had a decent pace. It was okay. So if a particle moves from point 1 to point 2, I want to know how to express my potential difference. So I'm moving from this location out to this location. So this would be like my V final, and this would be my V initial. And I can calculate my V final. Right? My V final is equal to KQ over D. I'm going to call it D2 because it's at location 2. And my V initial is equal to KQ over D1. Or Or you can do DI and DF, whatever you want to do. I'll do DI and DF. Oh no, I'm sorry. Whatever you want to do. You get my idea though, right? That the distance to those particular points will tell us what is the potential. And so my change in potential is going to be VF minus VI, or I can think of it as V2 minus V1. That I look at the difference in potential between this point and this point. So batteries are labeled according to their potential difference. And it's the difference in potential between their two terminals. So like for example, if this is a 9-volt battery, usually what that means is that I have 9 volts here and 0 volts here. And so there is a potential difference, a delta V, equal to 9 volts minus 0 volts, and that's equal to 9 volts. And by the way, if I'm thinking about my potential, go back to this mountain analogy, the point up here where I have my positive charge would correlate to here, and then when it rolls down the hill, that would correlate to this terminal. High potential is the 9-volt side, low potential is the 0-volt side. All right, do you know how your house is wired? You have 2 different kinds of outlets in your house. You have one outlet that is at 120 volts. That's the one that you use most commonly. There's another outlet. Do you know what it is? No, it's not 0. 220 or 240. Some people call it 220. Some people call it 240. It depends on how you define the voltage. But the 240 outlet, or 220, is the one that you like plug your hot water heater into. Or you don't plug your hot water heater, your dryer into something. Huh? The big ones, yeah. Instead of having 3 prongs, they have 4 prongs. The reason is that you have this extra prong that is at negative 120. So you have one prong that's at positive 120, and then you have another prong that's at negative 120 volts. So what is the potential difference between 120 and negative 120? No, because you don't, 240, right? You don't add them, you subtract them. Right? Just like we did here. We didn't add 9 and 0, we subtracted 9 and 0. Yeah? 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 Okay, you're taking the final minus the initial. That's always a change in something, is that you're taking final minus initial. Okay. It's going to come up again, but I want to talk to you a bit about... Oh, no, let's see this. So, it keeps coming up. A charged molecular atom that's an ion, right? Either a cation or an anion, moves between 2 different points, perhaps across, I don't know, a cell membrane, maybe? So they'll move across a cell membrane. But that's just an example, right? I mean, you can have charged particles move across all different points in space when you have a difference in potential. And that object will experience a potential difference, and the energy of the charge will change as a result. And the energy of that charge is going to be equal to Q times delta V. It shouldn't be surprising that we've been defining V, as U over Q all along. All right? We've been defining V as U over Q all along, so U is equal to Q divided by V. I just cross multiplied here, right? So my change in potential energy is equal to my charge times my change in potential. And remember, if we think about these equations, U was KQQ over R. Excuse me, not R, D. Q right here, and then I KQ over D. Look, these are the same as one another. Right? They're the same because they're all coming from the same definition. KQQ over D, Q, KQ over D. These are identical to one another. And this expression just comes from this. This is not on your equation sheet, but this is. Make sure you look at that. There are about 6 or 7 equations, 8 or 9 equations on there that are important. Or, okay. 4, 5, 6, 7, 8, 9, 10, 11 equations on the equation sheet. Charges, positive charges, tend to move to lower potential. So this delta U will tend to be negative. For positive charges. All right, so mountain again, positive charge up here. This is a high U. This is a low U. It moves in this direction. If I want to know what delta U is, it's going to be my, we'll call this U2, U1. It'll be U2 minus U1. But notice, this is a small number where I have a low potential energy minus a big number where I have high potential energy. And so this is going to tend, for positive particles anyway, to be a negative number. Then positive charges will move so that delta V is negative. They will have a negative change in potential. That is decreasing potential. Not really saying anything new here. I'm just saying it in different words. But I'm still saying that the rock is going to roll downhill for positive charges. But what that means is that it's going to be a negative change in potential. That delta U and delta V will be negative. So decreasing potential. And then negative charges are just the opposite. Negative charges will move so that delta V is increasing. And that is an increasing potential. So if I have a negative charge, it's going to tend to move in this direction. Increasing potential, decreasing potential. Okay? So I will have a positive delta V, negative delta V. Because this is decreasing, the change in the potential is negative. Right here, my U is decreasing, my V is decreasing. They're related to one another. So my delta V is also decreasing, or is negative. My delta V is negative. Positive charges roll downhill, negative charges roll uphill. It's possible to move charges so that their energy does increase. Yeah. Why is this important? Oh, it is important. It'll come up again later. So it's possible to move charges so that their energy does increase. See, for both of these, their potential energy is decreasing. They're moving from a position of high to low potential energy for them. However, this requires some source of extra energy. And we'll see that in the form of the what's it called? The potassium pump? Potassium something pump. What's it? Sodium. Sodium potassium. Like when we move an object up in the gravitational field. And that's what that thing is doing, is it's actually giving those ions extra energy to move, if they're positive charges, to move the positive charges uphill, for example. It's like the roller coaster, chugga, 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 pulling the cars up to high potential, and then they go through the business that they do. Yeah, so this energy, when we move charged ions, so their potential energy increases, comes from the sodium potassium pumps. I've done nerve cells before. You know, some of these terms are not new, right? Like sodium potassium pump and cell membrane and the like. Some of y'all seen that at least? No, understand. The book goes into it, and we'll go into it too. But the book does cover those things fairly well. But we'll do it too. All right. Oh shoot, it's 10 after. I'm gonna hand back your test. I'll give you a few minutes. The tests are online. I just put them on the website this morning before class, so you can grab them there.